Let's discuss exercise 2. The solution has already been made available to you in the VLE. The first thing we need to do is to run this program. Let's also run the Python program. We'll now discuss the solutions briefly, emphasizing only on the method or the technique and on the interpretation. Prior to the main tasks, you were asked to import the data file, save it to specific variables, and then plot the data. For task 1, the goal is to determine the total charge of the capacitor from t equals 0 to t equals 0.1 seconds. So if you have a graph of the capacitor current versus time, then this is easily obtained by taking the integral of the curve for the current over the whole time period. Numerically, you should apply the trapezoidal rule, which was given and is shown. You can do it in two ways. Implement the first equation, which is what I did and what you're looking at now in your own MATLAB and Python softwares. You can also use the second equation and do this. I start with I equals 2 and reduce the number of data points because I'm only going to sum this portion from I equals 2 to n minus 1. So I write this here as sum q equals sum q plus cur of I. And then I also need to add this one here, which is f1 plus, and then I have to multiply 2 by this sum 2 times. Then finally add the last one, sorry, this should be cur. Add the last one, which is cur and length of cur minus 1. Okay, close parenthesis, and of course divide everything by 2. So if we run this, we get the same result. Let's now do this in Python. So in Python, this is how we should implement this equation. So I begin from 1. Remember that in Python, the first index is 0 and the second index is 1, and that's where I want to begin. So even though here it says I equals 2, this sum actually starts from I equals 1, but in Python, the first index is 0, so that's why I have to use I equals 1 here. I also have to reduce this to one index less. And then I type in the new equation. I can just write cur and I. Okay, and I'll also add the first one here. So this is 0 plus, multiply this by 2 plus cur of np.size cur minus 1, closed parenthesis, and then divide everything by 2. Okay, you can see that we still have the same result here. MATLAB and Python actually has a built-in function that employs the trapezoidal rule. The function is called traps, which you should have already used in this exercise. As you can see, the calculation we did is pretty much accurate compared to MATLAB and Python's built-in function. The next task is to obtain a time dependence of the capacitor charge from the graph of the time dependence of the current through the capacitor. If we knew the function, then we would be implementing this the same way as we implemented things in the video examples. But we don't know the function. Instead, what we have is data generated from experiments that kind of looks like the expected theoretical functions. This is what you typically get when you do measurements. You should be able to process discrete data even without the knowledge of the function that fits it. It turns out that this is easily implemented using the function cumtraps, or cumulative trapezoidal. As in the traps function, there are two differences between MATLAB and Python's cumtraps. One is that the x data is typed in first in the MATLAB version, while the y data is typed in first in the Python version. Second is that the MATLAB version retains the same number of data points as the integrand data. As you can see, both cur and q have exactly the same sizes. In Python, q, which is the output, loses one data point compared to the original variable cur. Thus, for MATLAB users, you didn't have a problem with adding one data point to the variable q later on when you did the table or when you saved the data. Python users needed to take this into account when plotting and when saving the data. Moving on to task 3, where we compare the experimental data with theory, we see these two equations for charge versus time and current versus time. In the figure, we use circles and asterisks for the discrete data and we used a line for continuous functions. We can see that for the charge versus time, the charge does not saturate, as we should expect from theory. For the current versus time, we notice that the curve theoretically approaches zero, while experimentally there is still some leftover current that is fluctuating. The origin of the fluctuations in the current can be attributed to external noise due to several factors, one of which is the voltage source itself. This is also the reason why the charge does not flatten with time because of some transient current. The next task was to differentiate the experimental charge versus time and compare with the experimental current versus time graph. We can see that the results agree quite well, and that using a simple, straightforward divided difference already did the trick. Finally, the last task basically teaches you how to save your data to a text file. In both MATLAB and Python, you can save your data to other formats, including Excel format. Before we end this discussion, I would like to scroll back to our trapezoidal algorithm. While MATLAB and Python already has built-in functions, it is not complete. Thus, it may be useful for you in the future to make your own functions and use it for your own purposes. So what we're going to do is to make a new function that uses the algorithm you used for the trapezoidal rule. First, let me show you how to do this in MATLAB. The first thing we need to do is to open a new script. The syntax for making a function is this. First you type a function, and then you type the output variable. So let's say outvar. And then you type the function name. So let's call it mytraps. And then you type in the arguments or the input data that you want in order to implement this function. So what do we need? First, we need this cur, and of course, we need the step size h. So I would like my traps to have two arguments. The first argument being the function that I want to integrate, and then h being the step size of the function. Okay, type end to terminate the function. Okay, now I can write my function here. So let's save this first. So notice that when I saved the file, it already recognized what the function name is. And this is important. What's important is that the file name must be exactly the same as the function name. Otherwise, this function will not work. Second thing that is important is that I'm going to use this function in this file, numintdiff solution.mlx. And this file is located in this directory, exercise 2. So it's important that this function is in that same directory. Otherwise, when I run the function here in this program here, it will look for this function, and if it doesn't find it, it will produce an error message. So I save that. Okay, and I replace this one. Okay, so what I do now is to simply copy this one. Okay, paste it here. Okay, and then of course the tabs doesn't matter, but of course it's just if you're OC. So sum q is still starts from 0. Now here is the file name or the data. I can change it actually to data if I want, but I need to change everything to data. So and this one also. Okay, and then the output variable should be outvar. Okay. So now I save this. Okay, and this should be ready to use. So I comment this out, and then I use q, the variable q. I assign the variable, the output to the variable q, and then I use my traps. Okay, and then cur, and then h. Okay, so what this does is I call out the function which I made, and then I assign this variable cur to this variable data. And then I also assign the variable h, whatever the value of h here is, to this h here. Okay, now it doesn't matter if it's h here or if it's another variable here. Okay, whenever you use something like this, then whatever variable is inside this function is a local variable. This means that it's only used to this specific task. Okay, so like for example, sum q data and outvar and h is only used for this function. You will not see this in the workspace when you run the function MyTraps. Okay, so let's try this. Okay, here's the error. Okay, and save that. Okay, and then run this again. Okay, now you see that q is equal to 0.006. Okay, it says here outvar, which is this one, and it displayed the output because I didn't put a semicolon here. So I put a semicolon there, and then I run this again. Okay, you can see that it doesn't display the variable outvar. Okay, since it's a local variable. You can see that you don't see the variables in MyTraps like SumQ or data or outvar here in the workspace. So these are global variables, and these variables that are used here are local variables, local only to this function. Okay, now let's do this in Jupyter. So to do this in Jupyter, this is the syntax. Type in def, and then I type in the function name, which is MyTraps, and then I type in the arguments. Similar to what we did, we use cur and also we use data and h. Okay, and then semicolon there. Okay, the next thing we need to do is to use this, some q, then this, and of course this. Okay, I remove this. I'm going to remove this now. Put everything back to the way it was originally, and compute for q. So this should be just some q, and then I return q. Now the difference between what in Python and MATLAB is that here I didn't need to put a variable, an output variable, while in MATLAB we needed to put the variable outvar. Okay, so let's assign q to be equal to, now let's call the function. Okay, save this. Okay, and then we run it. Okay, you can see that it produced the same result as in the traps and as in the previous example. Again, whatever is inside this function is local only to this function. So these are local variables. So this q is not at all the same as this q, because this q is this variable q is a global variable, while this are local variables which are only used in this function. So that's how to make your own function. I hope the discussion on the solution to exercise 2 has been helpful, and I also hope you've learned something new as well. If you have any questions regarding this lesson, send me a message through the VLE or via email, or drop by in our Zoom or Discord sessions.